Welcome to my presentation. Good afternoon, everyone. My name is Jaroslav. I gave this talk a bit of an ambitious title, and when I started working on the slides, I had some hard times actually fulfilling everything that I promised here, but in the end, I did manage. You will get a little bit of nuclear reactors, you will get a little bit of pretty pictures, and you will get lots of 3D printing. So the talk is really about, mostly about 3D printing. The rest is just on top of it. And the one main message that I want to deliver here, if you want to call it a take-home message of this talk, would be that the same technology that we use for generating realistic images, pretty pictures on the computer, and the technology is based on accurate physical-based simulation of what happens to a light in an environment. The same kind of things are actually extremely useful when you want to do accurate 3D prints, such as the ones that you see here in the image that I'm showing. So before I start, I'll just start a little bit with my background. I'm a professor at Charles University in Prague and one of the founding partners of Corona. And I've been in this business of graphics and mostly rendering research since 2001, so it's been a while. I started at the Technical University in Prague, then I moved to Cornell for 2 years. That's the place with the famous Cornell box. It's still there, somewhere covered with a lot of dust in the corner of the measurement lab. And then I moved to Charles University in Prague, where I started a research group some 8 years ago. And of course, since computer graphics is an applied science or applied research, we've been doing quite some collaboration with industrial partners. So I've put my hands on the code base of Arnold. Back in the days when before Solid Angle existed, when Arnold was still part of Sony Pictures Imageworks. We have an ongoing collaboration with Weta Digital, so if you have seen any of their films in the last couple of years, starting with Hobbit, you have probably been watching results of some of our technology, and we have also transferred some of the tech into Pixar. And if you work with Substance Designer, the real-time preview with IBLs and complex materials, that's also our work. Okay, so this is kind of an overview of what I've been working on in my kind of academic research. Things have changed a lot in 2014 because Ondra, Adam and myself started Corona, and at that time I made the decision to keep my position at the university, and this turned out to be a happy one because there's been a lot of, let's say, synergy between the two. Corona has benefited from this quite a bit. Half of our development team are my former or current students, but also it's been great for the students at the university to be able to work on topics that are really practical as opposed to working on things that you do just for the sake of being able to graduate. So that worked a lot. And again, in 2017, last year in summer, we joined forces with Chaos Group. So right now I work on longer-term research topics that should eventually cater to the work that we're doing together between Corona and Chaos Group. I also like community, so I run these barbecues, graphics barbecues in Prague. This is the research community, so it's not the artist community, but there's a lot of research and education in graphics going on in Prague and in the Czech Republic. We also run this winter conference every year. It's a great conference because you spend the entire day skiing and then you listen to a few talks and then you drink till 2 a.m. and you do it for 3 days and then you rest for the rest of the month because you can't take it anymore. So this is Vlado and Asen were my last victims from the beginning of this year. So, okay, so this was just an introduction, okay. So, what's on the agenda today? So, I will very, very briefly talk about rendering. Then I will move to the 3D printing part of the talk, which is really the core of what I wanted to talk about. Then, in order to deliver on that promise of a little bit of a nuclear science. I will get back to rendering, and I will just briefly mention some current research at the very end of the talk, time permitting. So, photorealistic rendering. Okay, I didn't know who I was going to talk about, but my assumption is that all of you know that currently we have technology that allows us to create some stunning photorealistic images of architecture, interiors, and it's also a technology that's been adopted some 5–10 years ago in the movie industry, and it has also contributed a lot to the improvement of the quality of the visuals that you can get in the movies. And you have lots of render engines on the market. You have some of them being developed in-house in the visual production houses. And what all of them share in common is really the main core technology, which is the idea that if you want to create something that looks like reality, you really have to simulate what happens in reality. And what we see is the light that strikes our eyes, so you need to run some fairly accurate light transport simulation under the hood in order to get a realistic image. And that is the technology that allows you to take your polygons, your materials, your light setup, and turn it into a beautiful photorealistic image. Okay, so this is just a brief intro, but the reason I put the introduction here is that I just wanted I wanted to bring up the point that the same kind of technology, the technology that allows you to simulate light propagation and light scattering in a scene, is at the very basis of accurate control of 3D printing. It's a bit of out of topic, but I'm hoping that you will enjoy it nonetheless. 3D printing, we've been hearing about it for quite some time now, and it has really found many applications in various kinds of activities, human activities. Some of them you can see here. But when you run in a random person on the street, start talking about 3D printing, then what you're probably talking about is this technology which is based on fused deposition modeling. You have the printing material is a plastic, it goes into the printing head, then it's melted, and the melted plastic is deposited on the 3D print where it solidifies again. And the big disadvantage of this technology is that if you want to switch from one material to another, you have to empty the printing head before you can move to the next material. So despite the fact that the producers of these kind of printers that are based on this kind of technology claim multicolor printing, what you can see here is that you really have like discrete pieces of the printout having different colors. And you cannot really have like a full colored image or texture on top of that surface. This is totally impossible, out of question, with this kind of a technology. And at the very end of the spectrum, you have a much more expensive technology that allows you to do exactly that. So this is photopolymer jetting or polyjetting for short printers that at the first sight, the technology looks more or less the same, but it's actually very different. The printing material comes and is a form of a photopolymer, some kind of a resin, and it's liquid. And it goes into a print head, which this time, it's actually a regular inkjet print head, exactly the same inkjet print head that you have in your inkjet, €100 inkjet printer at home. And that head actually deposits it, and then it shines some UV light on it, and it's a photopolymer, so it's curable by UV light, so it hardens, and you build the object layer by layer. The big advantage of this technology is that really every single voxel that you print out can have a totally different color. So you can create 3D prints out of a totally, the level of the visual quality that you can achieve here is on a totally different level. Okay, so here's just a couple of examples of the printouts that you can achieve with this kind of a technology. And so this is this is really exciting, okay? Because you have a technology with which you can do a lot, And we are at the stage where we really don't know how to achieve, how to use it, how to utilize it. Okay, so I mean, just this example here. Okay, so this is a detail of a 3D printed sushi. You can see that it still looks quite a bit different than a real sushi on the other side. So we have this new problem. Essentially, where we are with 3D printing right now is where we used to be with realistic rendering at the end of the 90s. Okay, so we have a potential, but creating something realistic, we don't really have the software technology, we don't have the knowledge, we don't have much at all. We have some hardware, but we still don't know how to use it. So it's a great opportunity for a guy like myself, because I like to do research. And so the problem that we're looking into is realistic appearance fabrication. So in the same way that we have realistic rendering on a computer where our medium is a 2D screen, here we have realistic rendering but in 3D. Of course, this is a more general problem than rendering for images, because what you want to reproduce is, you know, not just colors, but also translucency, surface finish, and so on and so forth. So you could define the problem that you want to solve as shown in the diagram right here. So can you see the? Yeah. So you have some target appearance. This is maybe some model that you've created in 3ds Max. This is how you want your 3D printout to look like. What you need to figure out, and that's the black box right here, is how to distribute the printing materials in the 3D print in such a way that when you actually send it to the printer, what comes out is something that's going to actually look like the target. And there's many open problems. Essentially, it's an unsolved problem. You have to start somewhere. So we have started somewhere looking into color and texture reproduction. It was hard enough. It still took us 2.5 years in a fairly large consortium of people supported by the European project Distro. I really like this project because it was the first European project where I think we actually did something cool. Before I worked on a European project, it was a total disaster. But this one worked out really well. Okay, so what we can do right now is flat prints with arbitrary textures on it. So you could say, okay, what is it good for? You know, why do you do 3D printing to print something flat? Well, because you really have to start somewhere. We're of course working on generalization to 3D right now, and it's hopefully going to be done by the summer. So this is it. The enabling technology is, as I said, the polyjetting technology. The top of the line printer in this area is the Stratasys J750 machine. Just to give you some idea, we're talking about 300 to 400,000 euro for this piece. Okay, so it's a really expensive technology. It's not something that anyone can buy at home, but you know, 5 years, 10 years down the line, it's probably going to become much cheaper. So this material can print with 8 materials at the same time, out of which we use 5 as the colored materials and 1 as the support material that holds the printout. So we have the usual CMYK materials as you have in a regular paper printer, and then of course we need a white material because there's no paper, there's no support. So if we want to see something white, we also need to add that material in there. And okay, so what I wanted to say on this slide is that these materials, they are supported by the manufacturer of the printer, and the line of these materials is called Vero Opaque, and they have one thing in common, and that is that they are not opaque. Okay, and they are not opaque at all. In fact, they are very, very translucent, and that causes all sorts of troubles. So currently we are actually very, very good at reproducing things that are translucent with 3D printing. You see the, the backlighting in the ears. You have, a marble-like Stanford bunny printed here, sushi, and so on. So whenever we want this to reproduce this translucent appearance, that's possible. But if you want to reproduce, a sharp texture, if you want to reproduce a given color, there's no technology, okay? So if you send this texture into the printer, what comes out is this, okay? So if you look at the plant here, all of the detail is gone. You look at the image and you see that it's totally blurry. You don't like it. The colors are off. That's another thing that I won't be talking about that much today. But of course, color reproduction, faithful color reproduction is probably the first thing that you want to sort out, and we did sort it out in our project. So this is kind of the vision, right? I mean, someone gives me a textured 3D object with texture of any quality, any sharpness. I just want to send it to the 3D printer and get something that's going to look just the way the model looked like. And so this is where we are right now. Okay, so this is impossible today, but we have made some progress. So these are the target textures that we want to render. And this is what happens if you take these target textures, you put them on a box and you send it in an STL file to the printer and ask it to print. So the default printer driver does this. Okay, so it turns something nice into something fairly ugly. Colors are off, everything is blurry, it just doesn't look right. And so this is something that comes out of our pipeline. So you see that we've been able to recover most of the sharp detail. Also, the color reproduction is much more faithful to the original. And the way we do it is by optimizing for the correct material distribution in the object. And kind of the motivation for this research is coming from the idea of pre-correction. Okay, so it's a general principle that you can apply whenever you have an optical system that has some difficulties, that actually implies some degradations to your image, and that you cannot find any work around it. So the best you can do is actually pre-correct that image such that when it's run through this degradation, it's hopefully going to look the way it was supposed to look in the first place. Okay, so this is one example here. It's a paper, I think, from 2014 from SIGGRAPH. And what these authors have looked into is pre-correction of images for myopic people. So people that you show this image to that person, and this is what that person is going to look like because of the impaired vision. And you're wondering, okay, so what can I do? Okay, so first thing, he can wear glasses, of course, but what if not, okay? So you're wondering, what can I do to this image so that when I show it to that person, he's going to actually look something that's going to look all right. And this is the thing. This is the transformation. You're kind of like undoing the degradation that happens due to the out of focus side, essentially. So you show this, let's say, sharpened image to that person, and he's going to see this. And that's arguably something that is much closer to the original than what that person would see if he or she was shown the original image. So that's the idea of image pre-correction, and that's kind of the idea with which we've started our project. We knew that there's a degradation of the image quality, which is caused by the fact that there's translucency of the material, there's a lot of light scattering happening inside of the object, and because of this light scattering inside of the object, everything gets eventually blurred. And we cannot undo this. We cannot stop nature from doing this. This is what happens with these materials, and producers don't know how to create more opaque materials. These are the most opaque materials that we can produce today. So what can we do about it? So the idea is to, again, apply this image pre-correction, but this time it's a more difficult problem, because instead of pre-correcting a single image, your task is to figure out really the full volumetric distribution of the individual printing material inside the entire volume of the object. Of course, we've tried at the beginning just a pre-correction of the image, extruding the pixels of the image inside of the object, but it didn't work. Many things that we've tried didn't work in this project, and every time when you work on something, you have no idea which way to take it. It's exciting, but it's also frustrating because you have to try so many things before something starts working. So this is the final pipeline that we came up with to address this problem. So first of all, we need some optical characterization of the printing materials. We need to know how much light they absorb, how much light they scatter, and what is the directionality of the light that they scatter. The second thing that we have is the target appearance. And then we run this through this magic box that I will be talking about. And out comes the distribution of the materials inside of the entire volume, which is then sent to the printer, printed out, and you hopefully get something that looks close to the target appearance. And so what happens in this optimization box is a simple iterative procedure where you have some guess of the current guess of the solution. And with this guess of the solution, you run a lighting simulation which gives you a prediction of how the object would look like with this material distribution. Then you compare it to the target appearance and you see that it differs, so you correct the material distribution and you keep doing this in a loop until convergence. So these are the three main building blocks that I would like to talk about a little more. So the first thing is the optical characterization of the 3D printing materials. And we wanted to build something where people really can, at home, measure their printing materials. So something that anyone can build at home. Okay, so it's a camera, it's two lights. And what we do is that we print out thin slabs of the material, and we glue them on top of a checkerboard pattern with the gel that you can actually buy out of a regular store, which just happens to have index of refraction which more or less matches the index of refraction of the material. So there's not that much bending of the light rays going on. You can ignore that effect, okay? And so what we then do is that we take color-calibrated images of these configurations, and we just cut out this area where the printing material overlays the dark and bright pattern. And what we get is this. And when you look at the printout like this, you see as you move along the vertical line that there's some kind of a profile. So for a bunch of a couple of pixels, it's going to be dark. Then somehow it's going to fall down, go up, and the luminance is going to be brighter. And the same thing for all the other materials, just in a different way. And what we have found out is, okay, and this is what these profiles, when you actually plot them, this is what they would look like. And what we have found out is that the shape of this profile is a really good signature for the scattering parameters of these printing materials. So we have been able to pre-simulate these profiles, a huge library, a huge dictionary of these profiles for all sorts of different scattering parameters that the materials could have. And we observed that they are very, very different, okay? So then when we measured these real materials, we could just take the profile and look up our library of profiles to see which matches, and from that we just read out the parameters, okay? So this is pretty simple. And this is where the light transport simulation really kicks in. If you want to do something like that, you have to have a way of simulating what happens to the light in a setup like this, okay? And this is, you can run Corona, you can run V-Ray. We ran a research render called Mitsuba, but it's the same idea. I mean, we could have done it with just about anything, okay? So really, the faithful simulation of light transport is an important building block in being able to solve this problem. Okay, so we finished it, and this is the acquired images. This is what we get out of the simulation. It's a nice match. okay? And that's for the 1 millimeter thickness, matching really nicely, okay. So now we have the scattering properties of these materials. So whenever we have some distribution of the materials in the volume, we can just use our rendering system, our predictive, physically based, super accurate rendering system, to predict the appearance of the 3D printout given any material distribution. So what you have to run here is really an accurate subsurface scattering simulation using Monte Carlo path tracing, which takes ages, but what comes out of it is something that looks extremely, extremely good. Okay, so these are color managed pictures of the 3D printouts, and these are our simulations, and you cannot see any difference. Okay, so really the rendering is a highly accurate predictor of what the printout is going to look like when you send it to the printer, and that's what we needed in the first place. Okay, so finally there's this last step, the solution refinement. So that's okay. So what you get here is the prediction. You see that it's different from the target, but what do you do now, right? I mean, how do you change the material distribution to get closer to the target? So it's not clear, and before I give you some details on how it works, this is kind of like an outline of what happens during the iterations of the algorithm. So we initialize it by essentially copying this input image into the topmost layer of the printout, while everything below it is left white. And I will explain in just one slide why we decide to initialize by essentially making everything white. So if you put that image in just the topmost layers, you get something that is totally desaturated. Why? Because the light just penetrates through the topmost layer, then it gets into the white, loses all the saturation, and you get almost nothing. And so as the algorithm progresses, what we do is that we make the topmost layers more and more contrasting, and we also propagate the dark materials down through the stack of the materials. And as you keep going, the algorithm converges closer and closer to an appearance that matches your target. So there's some optimal ways in which you could do this refinement of materials that you can take from optimization literature. That would mean computing gradients of a function over a billion-dimensional domain or something like this. You really don't want to do it because like each voxel of your printout creates a dimension. You want to know how to shift it, so you need to compute the gradients. And okay, this would be crazy and it wouldn't be feasible at all. So we went for a heuristic, and the heuristic was actually quite simple. We just looked at printout, we took a texture, we extruded it into an object into the depth of 0.5 millimeter, 1 and 2 millimeters. And there's a very simple observation that you can make here. The deeper you go with the extrusion of the color, the more saturated color you get. It's pretty obvious, but okay, it's good to see that it really works that way. But you have to pay something for this increased saturation, and that's actually that the white areas are more polluted by the green color. Okay, so you want these leaves to be totally white, but the deeper you go with the green color, the greener and greener the white areas become. Why? Because of the internal scattering. And there's more and more internal scattering of the light going on, bouncing between the white and green, and so the green kind of pollutes whatever you wanted to have white in the first place. So the idea is to start off with something that is as white as possible, because preserving white is the most difficult thing, and then only add dark materials if you absolutely must. And if you do add some dark materials, you also do this kind of erosion where you kind of like dig under the under the dark detail, so that not that much of the dark color pollutes the bright color. Okay, so this is how the optimization works. Okay, so this is it. This is our pipeline. Then finally, we have the solution. We send it to the printer, and this is the kind of results that we get. So these are the target images. This is what we want to. Achieve. And this is what you get straight out of the printer. This is the current state of the art. This is what Stratasys sends you. You pay 400,000 euro for a printer, and they give you software that produces this. Okay, and this is what happens when we apply our color management pipeline that I didn't talk about, but it improves the reproduction of the colors, but still doesn't apply anything to prevent the blurring. And so this is just unsharp masking applied to the input images. And this is a simple solution. It recovers some of the sharpness, but definitely doesn't achieve as much detail and as faithful a reproduction as what we have done here. Okay, so if you, long story short, before, after. Okay, so great, we can do colors and we can do textures in 3D prints. This is actually quite interesting. So this is what would happen if you shone a line of kind of laser light over the printer. This is what the result would look like on the if the printout was purely white. So you have the spreading of light because of the internal scattering. And this is what happens on an uncorrected print, and this is what happens on our print. So you see that on the uncorrected print, you have much more spreading of the light, and somehow magically our optimization achieves a result which spreads the light much less. Okay, so and that is the very reason why the result becomes sharper. Okay, so take-home message from this 3D printing excursion is that you really need to apply lots of knowledge from light transport if you want to produce accurate 3D prints, because all the printing materials are translucent. There's very intricate light scattering going on inside of the object. It's much more complicated than what happens with light as it strikes a 2D print. And if you don't apply the knowledge from light transport, you will likely get something that doesn't look right. Okay, so I am excited about it because I've been doing light transport for a long time, and I have to say that over the years I got a little bored by creating images a bit faster, or and now you have something where you can actually apply this whole knowledge, this whole body of knowledge that you acquire over many, many years of work, and you can apply it to a new problem. It's very exciting. I like it. Okay, so we worked on this with Max Planck Institute on Informatics. They have a cluster of about 200 machines, so it's about several thousand cores. Still, each iteration takes like 5 minutes, so it would take, I don't know how long it would take on a single machine. Like this is not something that you can run on a single machine. Okay, so we definitely need a way to speed up the whole process. We're thinking about machine learning because that's what you do today. And we're hoping to be able to speed it up by at least several orders of magnitude, because otherwise it's never going to be fast enough. And of course, generalization to 3D geometry, it's about 3D printing. If you only could print out slabs, it wouldn't be useful at all, right? So, but that's the 3D, that's something that we're currently working on. We already have results. It's looking actually quite good. The speed up, it still needs some care. I have some more time, so let me carry on. So, since the title of the talk promised a little bit of nuclear reactors, I felt obliged to get back to that topic. But in a way, it has a very tight connection to also the 3D printing that I've been talking about so far. So I will just go back to this slide with light simulation. Okay, so generating images, there's light simulation. 3D prints, there's light simulation. And essentially, all this light simulation takes ages. You need lots of computational power to get your image out. And if you don't, then you get a noisy image. So essentially, you have two ways of sorting it out. Either you subscribe to V-Ray Cloud when it starts working, really. It's almost working. The demo, I saw the demo today for the first time, and I think it was really amazing. Anyway, so either you subscribe to that, or you ask your developers to put some smart algorithms into your render so that you can reduce variance in the same amount of computational time. So this is an example of a paper that I have done with a student of mine that was published 2 years ago at SIGGRAPH. But what I want to show here is that really by improving the algorithms, the kind of speed up that you can get is really amazing very often. So there's many aspects in this variance reduction work that you can do in the algorithms, and you always take a small kind of piece of the puzzle and you focus on it and you try to improve it. So the one thing that I would like to briefly mention here is the work that I have done before joining Corona. So this is something that I have done during an extended visit to Weta Digital in 2013. And it was work on subsurface scattering. So, you know what this is? Anyone? It's a finger. Yes, it's a finger. And it's a finger. Sometimes people think that it's an ugly insect. Sometimes people think that it's some fruit. But it's a piece of a finger. And the reason why I'm showing this particular image is that it's a really good example that shows just how translucent skin really is. And so if you want to reproduce the appearance of skin, you better simulate very accurately what's going on with the light as it penetrates below the surface of skin. And of course, and without it, if you didn't do it, you wouldn't be able to reproduce these very, very typical visual effects that we just need on the skin for it to look right. Okay, so all these like red rims on the boundary between the lit and shadowed area and so on. And of course, there's a lot of approximate models that you can apply to it, but working at Weta, nothing is good enough. Okay, it's never good enough. That's they're just crazy. And what you get with these approximate models is usually lots of troubles when you have highly detailed geometry, so nose, ears. It usually doesn't work well. So they decided to go, you know, overkill. We have lots of machines. Let's do full-fledged Monte Carlo simulation for the light transport under the surface of the skin. So the way it works is that you enter under the surface of the skin and then you randomly walk under the skin, hoping that hopefully you will emerge back on the surface and continue tracing toward the light source. And of course, this doesn't sound like a super smart idea, because why would you do all this walking deep below the surface if what you're interested in at the end of the day is what happens on the surface? So we started thinking about how we could somehow inform the algorithm to just go back to the surface, do something. So I just tried a few simple solutions off the top of my head, and they always made the solution even much worse. And then I started looking into literature. And if you start looking into literature, I mean, after working 10 years in rendering, you know all the literature in computer graphics. So when you start reading, it means that you start reading outside of computer graphics. And what I started looking at then, thanks to my friend and colleague Eugene Dion, was literature on neutron transport. And we have found out that actually they solve very similar problems in the design of nuclear reactors. And the particular problem that they address there is the shielding of the reactor, where you're trying to build shield of a reactor is a mass of concrete. And concrete is expensive, and you have to pour it a lot of it. But of course, you don't want to put too much because then it would be expensive, so you have to run some simulations that tell you just how well the piece of the concrete shields the radiation that's impinging on the concrete from one side that you don't want to get through the shield. You want all that radiation to actually be absorbed by the concrete. And the ratio between the radiation, the radiation we're talking about is a stream of neutrons. And the ratio between the number of neutrons that are entering and that are allowed to leave is 1 in a billion. So if you run a Monte Carlo simulation, only 1 in the billion of the particles that you simulate will actually run through. If you want to get some reasonable statistical estimate, you need at least 1,000 that actually make it through. You're talking about tracing 1 to the power of 12 paths, and that's too much even for today's standards. But this is, of course, when we have been designing nuclear power plants for the first time, and we're talking about the 60s. Okay, so you really need to come up with something much smarter if you want to run this simulation here. And the idea was really exactly the same that we have with this skin simulation, which is, well, I have the radiation coming from this side. I'm simulating how the neutrons actually, what they do inside of the block of the concrete. But at the end of the day, I'm really only interested in the ones that make it to the other side. So can I somehow inform the simulation to actually proceed more likely toward the left-hand side than coming back? And people have been playing around with this idea. They call it path stretching, and sometimes they reported better results with path stretching and sometimes worse, and they didn't understand why it happened. And then finally, in '81, a researcher by the name of Dwivedi has been able to actually derive a theory for optimal path stretching. And the idea is very simple. If you know the approximate solution of the light transport inside of the slab, you have a provably optimal way of guiding the sampling decisions so that you minimize the variance of the computation, you minimize the error of the computation. And there's a really nice theory behind it. It's called zero variance random walks, and we're applying it in volumetric light transport and so on. But this specific case, in this specific case, we applied it for subsurface scattering. So the setup is as follows. We consider the part of the path that is under the surface. We kind of consider, for the sake of simplicity, that there's just white sky, uniform illumination. And in that case, if you have a semi-infinite slab of the material with a totally flat interface, which of course is an approximation, but why not? We are only looking for an approximate solution. Then the solution of the distribution of light intensity under the surface can be described as a function of the depth and the angle of the direction of the light. And this, another smart person back at the beginning of the 60s was able to actually derive a closed-form formula for this. Okay, so you have a formula that you can just evaluate and you get the solution. Okay, you don't need to run V-Ray. You know the solution just by evaluating some formula. It's in this specific case, but it's cool because you have a good approximation of what you can use. So the whole formula is actually quite complicated. So you cut some terms that are less important and you keep the important ones, and you plug it all together and you get variance reduction. So this is something. These are results coming from Weta Digital. You would expect something looking much better, but I mean, this is the only thing that I could take out of the company. But you see that the reduction in terms of variance is very nice. You pay essentially nothing for it. So this is one example of how you can somehow import knowledge that people have developed in a totally different field, tweak it just a little bit, and apply it in computer graphics for saving the planet, because you don't need to waste energy on running all these render cores. Okay, so we developed this back in 2014. 2013 at Weta. It's in use, as far as I know, since then for all the movies. And recently, I have talked to people at Disney. They use the same thing. And I have seen a report from Pixar where they describe that they are switching over to this technology. So everyone in the high-end studios, everyone is using this thing today. So we're going to the end of the presentation. Okay, so the rest is just really high-level sketches. So in this part of the talk, I try to make the point that if you know an approximate solution of light transport, of the light solution, if you know how much light is coming from where, how much light is where, you can really optimize your simulation and get results much, much faster. And in the previous case of light transport in the subsurface scattering, we have been able to find an analytical formula that gave us this approximation that we're looking for. But this is not always possible because general 3D scenes are just too complex for any analytical solutions. So the idea is that you can actually employ the partial result of your rendering to get these approximations, use them for sampling, at the same time refining these approximations, and eventually getting something that converges much, much faster. So back in the days where Ondra was still a serious PhD student working, he's saying no, he's always been working on Corona, yeah, I know. Anyway, so Ondra and another student of mine, Jirka Vorba, who's now working for Weta, by the way, they have worked on this idea where they actually implemented this in a way that they use some techniques from statistical learning, from machine learning, to actually learn the distribution of light in the scene as you progress with the rendering to achieve some really impressive speed up. So this scene here, this is bidirectional path tracing after, I think, 1 hour of rendering. And this is the noise reduction that you get by applying this algorithm. Jirka kept working on it after that, and he managed to improve it still much more. So, for example, in this dark area, you see that the noise reduction is really very, very nice. So recently, so we've been really encouraged by seeing how well this general idea works, and we decided to apply it also to Corona. And the one dispute that Ondra and I have been having since the very beginning is that Ondra has been always saying that direct illumination is the cause of all the problems. I've been saying, no, it's the GI, whatever. We have started working on direct illumination. Okay, so applying this idea of statistical learning, we have developed a new light solver. This is currently in the experimental version included in the current version of Corona. So you have to go and click the checkbox because there are still some engineering problems that need to be sorted out. But generally, this works extremely well. So this is a scene that is illuminated by the sunlight from the outside, and then some area lights here. But the sunlight doesn't really reach most of the visible area of the scene. However, the old light solver and most of the light solvers out there wouldn't actually know about it. They would just keep sampling the sunlight just because it's so freaking bright. And they, at the expense of sampling the lights that actually contribute here. And that would cause all the troubles that you can see in this scene. So by applying this new solver, you get a much cleaner image in the same amount of time. So again, this is the original and this is the new solution. Of course, this is a result in a SIGGRAPH paper, so it's been highly tweaked to show the best possible results. But generally, like in the scenes that you get in production, the speed up is still very, very good. And this is going to be presented at SIGGRAPH 2018, so it's a full paper at SIGGRAPH 2018. By the way, Asen will be presenting the dome lights at SIGGRAPH, and also Ondra, Vlado, myself, Henrik Jensen from Keyshot, and Thomas Ludwig from Indigo will be presenting a course on rendering for architectural and product visualization, so be sure to come to SIGGRAPH. Okay, another thing that we've been working on is intelligent caustics. So again, we're going with this idea of let's learn from what's happening in the scene to get a result that is fast and that doesn't require any settings. Okay, so going with this idea that Ondra was talking about in the previous talk, we want caustics, photon-based caustics, but you will not have to set any number of photons, you will not have to set anything. The algorithm will figure out everything by itself. So this is an image coming from, say, vanilla photon mapping solution, and this is our current result. Okay, it's not the most beautiful image on the planet, but it's a research prototype, so take it as such. So again, this is the original, this is the same thing in the same amount of time with just half of the photons. Okay, so this is hopefully coming out in Corona 3, if time permitting. And another thing that is kind of exciting to me, and everyone is playing around with deep learning, the idea of stylization. Okay, so you can play around with this online. I forgot actually what the name of the tool is, whatever. So this is your original image, and this is the style, and this is the stylized image, where you have applied the style to this image, and this comes out. Okay, and it looks pretty cool. But then you type architectural sketches into Google, and out comes this. And you start looking into these images, and you see that they have actually much more regular structure than what you get here. And if you apply this technology to this, you wouldn't get anything reasonable, right? So the big kind of dream that we have is that I would be able to get, a user would be able to get this sketch and say, why don't you render my scene in this style? Okay, and this is, it's a very difficult problem. I don't know if we will be able to solve it, but we're definitely doing some progress toward this goal, and there will be some intermediate steps, and hopefully a few years down the line we will be able to deliver that. So I am at the end of the talk. To my surprise, I've managed to finish in time. I would like to thank all my students and collaborators. Special thanks to Oscar for providing many of the 3D printing slides, because he was the man there. Funding agencies, and Total Chaos for running the show, and you for being here. Yeah, thank you for your attention.